Well, hello students. I'm going to do a review for our AP Precalc class, and this is for lessons 2.9 through 2.15. I'm going to work through and explain and coach you on the problems that are in the 2.9 to 2.15 end of Unit 2B review on flipped math. Most of you that are watching this that are my students are using flipped math in your St. Johns County High School AP Precalc class. So maybe your teacher has handed this out to you, but it is available at the Flipped Math website under the AP Precalc class. So I'll work through these and give you some explanations as we go along the way. So the first function here, they tell us to find the inverse function, f inverse of x. And as you can see, it is a logarithm equation. So the way that you always start any kind of problem that involves finding the inverse is to swap the x and y variables. So this f of x represents the y variable. And so I'm going to swap it for an x, and this x will become a y. And once I've made the swap of x and y, I'm now going to proceed to do the algebra steps to solve it for the y variable once again. So I'm going to first, like any other algebra problem that I'm solving, I've got to get rid of this term of plus 8 first, because I have 3 times log base 2 of y. And if I'm going to solve for y, I have to first isolate the logarithm portion. So I'm going to subtract 8 and divide by 3. So I get x minus 8 and then divided by 3. And on the right-hand side, I have log base 2 of y. And then this is one of the main themes of this unit, is how do we use logs and exponentials in the process of manipulating equations? Well, if I have a variable that I'm solving for and it's inside of a logarithm, then what I'm going to do is I'm going to exponentiate with the same base of the logarithm. So I'm going to raise 2 power on both sides, because 2 raised to the log base 2, that's an inverse operation, and they will cancel, leaving me just the y. So this will become y equals 2 raised to the x minus 8 over 3. And then as a last step, I do want to use the proper notation. So I'm going to change this y into the inverse function notation. So I'm going to say inverse function of f of x is 2 raised to the x minus 8 over 3. And what this notation tells us then is that this function here and this function that we started with up here are inverses of each other. All right, let's move to the next problem, number 2. It says, what is the solution to the equation 4 times 2 to the x plus 5 minus 10 equals 22? So I'm going to solve this for x. It's an exponential. My goal in solving an exponential equation is really first to do the algebra that is necessary to isolate the exponential portion. So I got to get rid of the minus 10 and the 4. So that's going to come about by adding 10 on both sides, which will give me that. And then I'm going to divide both sides by 4. All right, now there's 2 ways to go about this at this stage. Hopefully you recognize that the right-hand side of the equation, which is 8, can be written in the same power as the base of the exponential on the left, that is, as a power of 2. Excuse me. So my next step could be to write this as 2 to the x plus 5 is equal to 2 to the third power. And then for this equation to be true, the x plus 5 has to equal 3. And then my answer is 3 minus 5, or negative 2. Now, there is another way that you could have gone about that. If you didn't recognize that 8 could be written as a power of 2, what you could have done is say, well, I'm going to take the log base 2 on both sides. Right? This is where the inverse operations of logs and exponentials come into play. That if my variable is up in the exponent of an exponential, and I'm trying to solve for that variable, and I need to get it out of the exponent, I'm going to use the inverse operation of exponential, which is a logarithm, and I'm going to use a log that matches the base of the exponential. So really what you'd be doing from an algebra standpoint here is taking log base 2 on both sides. So the equation at that point would look like this. You'd have log base 2 of 8 on the right, log base 2 of 2 to the x plus 5. But those are inverse operations, and it leaves you x plus 5 equals log base 2 of 8. And then you subtract 5 on both sides, you get log base 2 of 8 minus 5. But you're supposed to be able to recognize this, students, that I'm going to write this a little bigger down here. Log base 2 of 8. You need to be on the lookout throughout your test on being able to simplify logarithms, because if you can rewrite this argument of your logarithm with the same power as the base of the log, then you can simplify it. So you're supposed to recognize that this is 8 is 2 to the third. And so this thing actually is a 3 minus 5. So log base 2 of 8 is 3 minus 5 gets me to my answer of x equals -2. And that's the same answer that we got over here. So that is my answer. When it comes to solving exponential equations, we don't have extraneous solutions. So when I get this answer, x equals -2, I'm done with the problem. I don't need to go back and check to see if it works in the equation. I mean, it's not a bad idea if you have time to go back and make sure that it actually is a solution by plugging it back in. But my point is, unlike logarithm equations, it is possible, or I should say, unlike logs, it's not possible for you to get an extraneous solution to your exponential. As you're going to see when we work with logarithm equations, it is possible to get answers that are not really answers. Those are called extraneous. All right, now we're going to work a problem that definitely is, I would say, maybe one of the more challenging problems to get completely right, and that is an inequality with logarithms. So here is what that's going to look like. I am going to condense these two logs on the left so that it gives me the natural log of x plus 10 times 5, right? So that is condensing those two logs into one log. And this is the natural log then still of 2x plus 17. And this is a less than or equal to here. And then what I'm going to do is I would exponentiate on both sides, right? ln, I'm exponentiating on both sides. It gets rid of the natural log. And now I'm solving this. X plus 10 times 5 less than or equal to 2x plus 17. So now I'm going to go ahead and solve this like I would a regular algebra inequality. So I have distributed the 5. I'm now going to move the 2x over to the left and the 50 over to the right. And we get finally x is less than or equal to -11. And definitely, if you encounter a problem like this on your test, that's a log inequality, you are not going to stop right here and say, I'm done, I solved the problem. It's more complicated than that. What we have to understand is that it is possible for some of these values that I'm saying are solutions here are probably not solutions. So what I would do is this. I would say, I'm going to start this off by saying, okay, on a number line, x is less than or equal to -11 means that I am saying that all of those values are solutions, like that. Now, what I want to do is I want to go back up to, I want to go back up here and see if this is going to, if these are solutions, these numbers that are less than -11, to see if they are solutions to this. And what happens here is this, students, that while my algebra told me that all the values less than or equal to -11 are solutions, I have a restriction up here. In fact, there's two restrictions, because this x plus 10, what has to be true for any solutions is that has to be greater than or has to be greater than 0, right? Because I can only take logs of numbers that are greater than 0, positive numbers. That's the domain of a log function. So x plus 10 has to be greater than 0. And not only that, but this argument, 2x plus 17, has to be greater than 0. This means that x has to be greater than -10, and this tells me that x has to be greater than -17 over 2. Now, where's -10? Okay, -10 on my number line is over here. So that means then that I can only consider all the numbers to the right of -10, and this says -17 halves. Well, -17 halves is about or is exactly -8.5. So it is in between negative. Well, it's even further to the right. It's over here, negative 17 halves. And notice this does keep going. There is no overlap of these three things, right? In other words, in order for me to have solutions of x that would solve this inequality, what would have to be true is there would have to be an overlap between these three things, because all three of these things need to be true for you to have solutions. That has to be true at the same time that that's true, at the same time that that's true. And since there's no overlap, those three criteria are never met. There's no solutions to this. Now, so my answer is no solution. Now, what would this look like? You wouldn't be able to do this on your test, of course, because you don't have access to Desmos, and you're probably, when you're working that problem, you're not going to have access to your graphing calculator. However, if I graphed the left-hand side, the natural log of x plus 10 plus the natural log of 5, and then I graph the right-hand side, which is the natural log of 2x plus 17, right? So this left-hand side here is the red line. So take a look at this. This is my graph. This equation here says, when is the red line less than or below my blue line? Well, you can look and see, never. The answer is never. That is never going to happen here. You can scroll all the way out here. So that's why there's no solutions, because there's no x values that would ever make the red line less than or below the blue line. So indeed, just being able to graph it on Desmos does help me see there is no solution to this problem. All right, let's move to the next problem. This says that Mr. Sullivan used to collect football cards. When the Cleveland Browns drafted Johnny Manziel, he just knew his rookie card would be worth a lot of money over time. Mr. Sullivan kept track of the value after every game that Johnny Manziel played. The data is shown below. So this shows me games played 1, 3, 4, 9, and the value of the rookie card was apparently going down. Okay, so Mr. Sullivan was wrong. The rookie card would not be worth a lot of money. In fact, as time went on, it decreased in value. And it says, what's a logarithmic regression equation that could model this situation? Well, it does make sense that this is a logarithmic regression, because if you take a look at what's happening as you move left to right through the data, is that the average rates of change are decreasing. So the function is, the values are decreasing, but they're also decreasing at a decreasing rate. I'm not going to go through the calculations here, but if you were to calculate the average rate of change of these pairs of points, these three pairs of points as you move left to right, you'll see that they are decreasing. And so that makes it a good candidate for a logarithmic regression. I'm going to go to my TI-84, and what we're going to do is we are going to go into stat edit, and we will put the data in. And I already have it in here into L1 and L2. Games played L1, value of the rookie card is L2. I'm then going to go to stat calc, and I'm going to run the natural log regression. That's number 9. The only log regression that you have in your TI-84 is an LN, or natural log regression, right? The next one is exponential regression. We want log regression. So I'm going to run number 9. My X list is L1. The Y list is L2. Make sure that you don't have anything in your frequency list. If you do have an L2 there, then hit delete to get rid of it. I am going to always store my regression equation into store reg equation by doing alpha trace and then enter on Y1, and it blows the Y1. This just means that when I hit this calculate button and it generates the equation, it's going to go ahead and automatically blow that into the Y1 equation in the equation editor, and I'll show you that after we do it. So I'm going to tell it to calculate, and it does the regression analysis, and it gives me the equation of the logarithmic function that would model this data. And that equation looks like this. Y equals, and it shows me a plus b times ln of x, where a is 57. When you are using your calculator, be sure that any decimal answers go out to 3 decimal places. So 57.400 plus b times the ln of x, and b is a negative, so I'm going to change this plus to a negative, and it's negative 17.736 multiplied by the natural log of x. And I am, just to be safe, if this is a free response question, I would say that y is equal to the value of the card in dollars, and that x is games played. Now, it does say, how many games would Johnny Manziel need to play for his card to be worth $10? Now, after I ran this regression, if I go and click on my y equals button, it does show me in y1, and these are just some stray equations I had from another problem, but it does show me in y1 the entire equation. So it took all of the a and b coefficients and it put them in. So there you can see there's my constant there, 57.400 and some other decimals, plus a negative 17 point blah 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 with a bunch of decimals times the natural log of x. So the equation is in the y1. Now this says, how many games would Johnny Manziel need to play for his card to be worth $10? So when you are doing a problem like this, don't just automatically assume that they're asking you to plug that value in for x, because they're not asking you what the value is when he plays 10 games. They could have said, what would be the estimated value of the rookie card when or after Johnny Manziel has played 10 games, and you plug 10 in for x, but it's not asking you that. It's saying, how many games will he have played when it's worth $10? I'm going to show you two ways you could do this. The algebra method would be to stick the 10 in for the y and solve the equation for x, and it would look like this. And it takes about 3 algebra steps to solve this for x. And I'm not even going to write all of the steps out. I'm going to do them on my TI-84. So the first step would be to take, I would subtract the 57.400 from both sides. Then I would divide by the negative 17.736, because my goal in solving for x is to first isolate the natural log portion of the equation. So over here, I'm going to take 10 and I'm going to subtract the 57.4, get an answer. I'm now going to divide by negative 17.736, which I believe is what that was, yes. And that gives me that number. I'll write the number down here, 2.67253. And that's equal to the natural log of x. Well, to solve for x, since my x is captured inside of a logarithm, I'm going to use the inverse operation of a logarithm, which is an exponential. So I'm going to exponentiate with the base of this logarithm. And remember, natural log is just a shorthand notation. It's a notation we use for log base e. So I'm going to exponentiate with an e, and I get x is equal to the 2.67253. On my TI-84, if I call up second function ln, it does use my e to the x function. It's waiting for me to put in the exponent. I will arrow up to highlight that answer I got, and then hit enter. It'll blow it into that exponent, and then I hit enter, and it looks like my answer is going to be 14.477 games. And so I would say, as my answer, I would say about 14 or 15 games is what it's going to take for Johnny's card to be worth $10. The other way you could do it is you could use a graphing approach to this. I think that method that I just did there is the easiest way to do it. But if you do go back into your equation editor, what you can do is you can graph a horizontal line for 10. And then we're going to look to see where that y equals 10 would come straight across and intersect that logarithm equation. Now, it could be a little bit difficult in that you have to set the window, perhaps, if we're going to graph this. So I'm going to set my window from 0 to about 15 games. And on the y, let's see what the y values end up looking like, right? The y values go from 57 and down from there. So that would tell me on my y window, I'm going to go from 0 up to 60. and then hit graph. Okay, so it's way over there where they intersect one another. I'm going to hit window and go a little bit further out here. I'm going to go out to 20, from x min to 0 to x max to 20, and then regraph it. And there's my intersection point. Now, to find the value of x right there, I'm going to use a command second function calc, and I'm going to call up the intersect command, and it's blinking on the blue, asking me, is that the first curve? And my answer is yes, it is. It's blinking now on the red. Is that the second curve? Yes. And I'm looking for the intersection, so I hit enter, and it jumps over there and it shows me 14.477, which is exactly what we got by using our calculator in a kind of in an algebra approach. So it shows me that that's where the two lines y equals 10 intersects. That just tells me the exact value of x when its y coordinate would be 10. There you go. Now, this technique of graphing two functions looking for their intersection point, it is something that we use quite frequently in AP Calculus. So it is a good idea to know how to use your TI-84 in this fashion to solve an equation by looking at the intersection of the left and right hand side of the equation. Because think about what I just did here graphically. What I did is I graphed the left-hand side of the equation and I graphed the right-hand side, and I looked for their intersection point. And the intersection point is the solution to that equation. All right, let's move on. Number 5, it says let A, B, and C be positive constants. What is an equivalent expression to log of a to the fifth, b to the second, all over c to the third? Well, they really should have better worded this by telling you to completely expand that logarithm. That's really what they mean. So to completely expand this, I'm going to first separate out the multiplication by addition, right? So a to the fifth times b to the second inside my log is going to get split out by addition into two separate logs. And since I have a c to the third in the bottom, that's going to be a subtracted term. So I'm using the properties of logarithms. So that's my first step in expanding, separating out multiplication by addition, and then splitting out the division by subtraction. So it really is as simple as, in this case, the factors that are on the top get a plus in front of their logarithm, and those factors that are in the bottom of your fraction inside the log, they're going to be preceded by a minus in front of their log. But for complete expansion, we do need to take those exponents and move them to the front. So the final answer is going to look like this, where I use the power rule of logarithms and move those exponents out to the front as factors. And that would be my final answer. Number 6, the function f is given by f of x equals log base 3 of x. The function g is given by g of x is log base 3 of 81 times x. Rewrite the function using properties of logarithms and explain any transformations from f of x to g of x. When they say rewrite the function, they're referring to g of x. So they want me to rewrite it with properties of logs. And then once I do that, to explain any transformations. Now, let's suppose that I didn't do any rewriting of the function. I still could tell you what the transformation is from the f of x to the g of x, right? We know from our work back in Algebra 2 and also our earlier work in, I guess it was in Unit 2 or Unit 1, I don't remember, but where we were transforming functions. We said that whenever you stick a multiplier in front of your variable x, that's going to cause a horizontal dilation. So you could say that this is a horizontal dilation by a factor of 1/81st. So whatever the multiplier is that's in front of the x, that is your transformation, the dilation is going to be 1 over that. So this basically, when you stick the 81x there, that is what we would consider a horizontal compression. Okay, because you're going to make it 1/81st as far away from the y-axis as it was before. However, that's not going to be our answer here, because they want us to use our rules of logs and expand this logarithm out. So I'm going to write g of x like this. it's going to be log base 3 of 81 plus log base 3 of x. This I know is the number 4, right? So this is what I was referring to you to earlier, that you have to be on the lookout for simplification of logs by matching the base of the log to the base of the exponential inside the log. This really is log base 3 of 3 to the 4th power. And when you have this match right here between the base and the base of the exponent and the log, they cancel, leaving you 4. So this really can be rewritten, g of x can be rewritten as 4 plus log base 3 of x. So now when I compare my f of x function to the transformed g of x, I now see that they're looking for the answer of it is a vertical shift up by 4. So that would be my answer here. Vertical shift up 4 is my answer. Now, it just so happens that these two right here, a horizontal dilation by 181st and a vertical shift up 4 for this transformation, they are equivalent transformations. But the one that they would be looking for, like on a multiple choice question, this would not be one of the options on the multiple choice. I'm certain of that. What it would be is they'd be wanting you to recognize the vertical shift up by 4. Next question. Number 7, using the tables below, determine if the data given is exponential. Explain your answer. Well, let's take a look at the data here. What I notice is that as I move left to right, my x's are increasing at different rates. 5 goes to 7, that's an increase in 2. That's an increase in 4. That's an increase in 8. So my inputs are proportional, it looks like. They are going up by a factor of 2 every time. So what can we say? What we can see here is that the inputs, when I look at the amount of increase, 2, 4, and 8, notice that these differences are going up by, these are multiples of 2. 2 times 2 is 4, times 2 is 8. This means that I'm going to write the answer this way. I'm going to recognize this is exponential, or excuse me, this is a logarithmic function. Let me get a better pen here. So we can say that x and y are in a log relationship because the x inputs increase exponentially while the outputs increase at a constant rate. So my outputs are going up by 1 each time at a constant rate, but yet my inputs are not at a constant rate. They're going up exponentially. Now, I'm not going to say that the inputs are going up proportionally because they're not proportionally, but the differences are proportional, right? So I'm going to redo that again. So these differences are proportional because 8 divided by 4 is 2, 4 divided by 2 is 2. They are proportional. So I could have said the x inputs, I don't want to say the inputs are proportional. I could say that their differences are proportional, which is the same thing as saying that they are going up exponentially. Let's look at B. Here, what's happening is the outputs are proportional because I am multiplying by 2 times 2, 2 times 2, multiplying by 2 again. So my outputs are proportional while my inputs are increasing at a constant rate. So this is an exponential function. So x and y are in an exponential relationship. And so my answer here is exponential because inputs increase at a constant rate. They're going up by 1 each time, while the outputs are proportional. Or you could say while the outputs are exponential. And then you go to problem C. And this says, when you look at this, notice that the inputs are increasing at a constant rate. They're all going up by 1, but the outputs are going up by a constant rate of 4. The differences are 1 here. The differences here are all 4. So that's linear. If the inputs and outputs are both increasing at constant rates, it's a linear function. However, if it were x and y, I would say that they are in a linear relationship. But what you're supposed to know from that last lesson, 2.15, is that if you're looking at x versus the log of y, and the relationship is linear, that means that x and y are in an exponential relationship. So we would say this: x and y are in an exponential relationship because it increases at a constant rate, and the log of y also increases at a constant rate. And so therefore, x and y are in an exponential relationship. I'll return to that idea a little bit later when I work some follow-up problems on this. This is the last problem of the review packet from the flipped math, and it says the function of f is given by f of x equals log of 3 minus x plus. Find the information below given for f. Well, notice they want the asymptote, the domain, the range, and the end behaviors, and a sketch of f. Well, I'm going to start with the sketch of f, because it's the sketch that's going to give me all of these answers. Now, you don't want to sketch a logarithm unless you know what the parent function looks like. The parent function, that is, what would log of x look like without any transformations? So this is something that you should know even from your Algebra 2 background, that there is a vertical asymptote on the y-axis right there, and the function comes from the asymptote, right? It's hugging this asymptote coming up and will pass through 1 on the x-axis and then slowly rise at a decreasing rate. So logarithm functions, this parent function is always increasing, but as you move to the right, as it goes out to the right, the rates of change are decreasing. It's getting flatter, never completely flat, but flatter as you move left to right. So that's what the parent function looks like. Therefore, I'm going to consider the sketch of this function by graphing it by transformations using these values that have transformed the parent function. Now, I am going to rewrite this because there's stuff going on inside the argument of the logarithm. It's 3 minus x. So for me to know what's exactly happening with this function, I do need to rewrite this as the log of. Now, I am going to put the x first always, so I'm going to flip the order here and call that negative x plus 3 plus 2. So there's a negative in front of the x. So I know that this thing is going to be reflected across the y-axis. Any function that you take the parent function and put a negative in front of the x is going to cause a reflection across the y-axis. However, since this is combined with a horizontal shift, which is what that plus 3 is going to do, it's going to shift this thing one way or the other. For me to know which way it's going to shift, I need to factor out that coefficient that's in front of the x. So I'm really going to write this as the log of negative times negative 1 times x minus 3. So it's going to look like that. Negative parentheses x minus 3. If you distribute that negative and flip the order, it's still the same thing as negative x. And of course, there is a plus 2 right here. So the transformations are, there's 3 transformations. I have a vertical shift up by 2. I have a horizontal shift to the right by 3. And the minus is going to flip it around the y-axis, meaning it's going to open up on the left-hand side of the asymptote. So when I sketch this, so I'll zoom out just a tad here. Maybe zoom in a bit here. Okay, so that'll give me a little bit of room here to make my graph. A horizontal shift to the right by 3 means that the asymptote is going to shift over 3 units to the right, over here at 3. So I know that my vertical asymptote is at the vertical line x equals 3. Now, this plus 2 over here, that vertical shift, I'm not really going to include that on my graph. It does shift the graph up by 2. I just want to know the general shape and direction of this graph. So I'm really not worried about the plus 2. The minus, on the other hand, is what was going to cause this thing to flip around the asymptote and open up on the left-hand side. So my graph is going to, of this function, is going to look like this. That's my function right there. It's got the 2 transformations of interest, the right shift 3 and the reflection across the y-axis. I now know that my domain is negative infinity over to 3. My range is all real numbers. Now the end behavior. Well, the end behavior requires me to consider what does it do out on the left side of the graph and what does it do on the right side of the graph. Well, on the left side of the graph, it's going towards infinity along the x-axis. So I will say the limit as x goes to negative infinity of f of x, and the y values are going higher. I know it looks like it flattens out, but it does keep increasing forever. So it is going to approach positive infinity along the y-axis. When I go to the right, though, I can't go all the way to infinity because the function stops when you get to 3. So the thing that I can do is I can say that the limit of my function as x approaches 3 from the left, because it does approach 3, but only on the left-hand side of 3. So we put this superscript minus up above right here. And therefore, what happens, right, as you come into 3 from the left side, those y values are all going down towards negative infinity. So those are my two end behaviors. Now, there is a corrective action assignment that you'll notice that's posted at the Flipped Math website for Precalc on Unit 2. And I'm going to work just a few of these for you. I think I'm going to work a couple of these log equations because these are the most challenging ones. I think what I want to do, and this actually is an error. Okay, this is supposed to be a 12. I did find that out when I was working this with a student. That's supposed to start off with a 12 right there. So I'm going to work numbers 2 and 3, right? I would say that this is maybe one of the more challenging type problems. Like I said before, inequalities with logarithms. All right, so let's try tackling number 2. If I'm going to solve a log equation, I do need to isolate the logarithm portion first. So I'm going to add 8 and then divide by 5. And after I do that, I get log base 2 of x plus 4 equals 4. Because I add 8, it gives me 20. Then I divide the 20 by the 5, it gives me 4. I'm going to exponentiate with the same base as my log. That gives me x plus 4 is equal to 16. X, therefore, is equal to 12. Since this was a log equation, I go back and make sure that the 12 doesn't give me a 0 or a negative number, and it does not. And so I'm satisfied with that as my answer. This says, number 3, what are all of the solutions to the inequality 3x minus 10? Natural log of 3x minus 10 is greater than natural log of 5x minus 28. Well, I'm going to exponentiate here. And that's going to give me 3x minus 10 is greater than 5x minus 28. Solving this, I'm going to, I guess I'll subtract subtract 5x from both sides, and then add 10 to both sides, and then divide by negative 2. I get x is less than 9. Notice if you divide an inequality by a negative number on both sides, you do need to flip the direction. Now, as we saw on the previous inequality, logarithm inequality, I can't just say, there's my answer, right? If this was a multiple choice problem, that's going to be an answer, and probably 30% of the students in your class will choose that and say, hey, great, I'm really good, I got this. Now, it's more complicated than that. Here's what we're going to do. We're going to plot my solutions on a number line. So here is where 9 is. This says less than 9, so it would be all of these values, because all of the values to the left of 9 satisfy x is less than 9, obviously. But there's two other things that have to be true for the x values to be considered a solution. This argument inside that logarithm, which is 3x minus 10, that has to be greater than 0, because this logarithm doesn't exist for 0 or negative numbers, so it has to be positive. And that means that x needs to be greater than 10 thirds. Well, where is 10 thirds? Well, on my number line. Well, 10 thirds is 3 1/3. So it's over here somewhere, right? I'm just saying that would be 3 1/3 or 10 thirds. And therefore, those solutions would start there and go to the right. But also, there's a third thing that must be true. And that is that 5x minus 28 must also be positive. That would mean that x needs to be greater than 28 fifths. Add 28 to both sides, divide by 5, I get x is greater than 28 fifths. Well, 28 fifths would be 5 3/5. Where is 5 3/5 in my number line? It's going to be in between 3 1/3 and 9. It's about here somewhere. 5 3/5, which is 28/5. That says greater than that, so therefore all of those. Now I do have, unlike the problem I worked on the original assignment here, the original problem on the inequality, there is an overlapped region, and it is the region from here over to here. That's my solution. The only x values that meet all three of those requirements are going to be from 28/5 to 9. So instead of me saying that x is less than 29, no, I'm going to give my answer as being from 28/5 up to 9. And I'm using parentheses for that interval because I'm not including the endpoints themselves. So I have to put those in parentheses. And again, that's not an ordered pair, right? This is an interval of x values. Solutions start at 28/5, excluding 28/5, and they go up to but exclude the number 9. Lastly, I want to take a look at some delta math problems that involve the semi-log plots that you learned about in lesson 215. This question says, determine if the semi-log plot of the data shown below represents an exponential model, then fill in the answers below. Well, because this data does not look to be linear, you can see it's got a definite noticeable curve to it. That would mean that the data behind this is not exponential, because exponential data, when plotted on the semi-log plot, will create a linear function. If it's a linear increasing function, that means it was exponential growth. If it is a decreasing with negative slope linear model on the semi-log, that would mean it's exponential, but exponential decay. So in here, and this is just simply saying that, making you walk through the logic here, the data does not represent an exponential model because the semi-log plot is not linear. If we ran an exponential regression on the data and then created a residual plot, we would expect to see, and they give you the word bank down here, we would expect to see a clearly defined pattern. So notice the logical progression here. Here it is. This is linear, or excuse me, this is nonlinear. Therefore, the relationship between the x and y variables is not exponential. So therefore, if you try to run an exponential regression on data that is not exponential, your residual plot will not be a good one, meaning you will see a pattern in the residual. I hope I said that right. I'm going to say it again in case I missed that. If I take data that is not exponential and I fit it into an exponential regression, and then look at the resulting residual plot, the residual plot will show a pattern. And that means that the original model that you picked was not a good one, because in a residual plot, we do not want to see any pattern at all. Okay, so that is definitely nonlinear. Therefore, the data is not exponential. If you take a look here, this is what we would expect exponential data to look like when plotted on a semi-log graph. And this is definitely linear, so that means the data does represent an exponential model. And again, don't think that, what are you saying? It doesn't make sense because linear is exponential. No, it's the reason that exponential data shows up as linear is because my y values are not on a linear scale. They're on an exponential, or what we call a log scale. So that means that the data was exponential. Therefore, the exponential regression that you would run to find the line of best fit would be a good model. It would fit it very well. And therefore, the residual plot would show no patterns, which is a good thing. We expect, if my model is a good one, we don't expect to see any pattern in the residual plot. And that, students, wraps it up. I hope that was helpful, and I wish you all the best of luck on your last summative on 2.9 to 2.15.